All right, let's just jump right in. There is so much buzz around AI today, but without a structured way to actually think about it, it honestly just sounds like magic. So, in today's explainer, we are going to strip away all the heavy jargon and build a crystal clear, incredibly easy to remember mental map of artificial intelligence so you can deeply understand how these technologies actually work. I mean, think about it. Are you using AI right now? Whether you're unlocking your phone with Face ID, checking Google Maps for your commute time, or even just getting a recommendation on Netflix, you are interacting with various forms of AI every single day. It's really not just some futuristic sci fi concept anymore. It's already the invisible layer powering our daily lives. And to make this super easy to remember, we're going to unpack this complex topic like a Russian nesting doll. Our agenda covers 1. The world of AI, 2. Machine learning basics, 3. ML categories, 4. Inside neural networks, 5. Deep learning architectures, and finally, 6. The generative AI era. Okay, section 1, the world of AI. Let's start with the outermost layer of our nesting doll. The crucial takeaway here is that any system mimicking human intelligence basically falls into this broad AI bucket. It's simply technology that allows machines to perform tasks that normally require a human-like brain. A really great example of this? Traffic cameras. Today, automated systems can instantly read the number plate of a speeding vehicle and automatically issue a ticket. That right there is pattern recognition, and it's AI at work. But here's where it gets interesting. Notice the contrast. Not all AI is actually learning from data. Sometimes AI is entirely pre-programmed with explicit, hard-coded rules. Take the fuzzy logic in your home air conditioner or a classic factory robot. Sure, they operate with a level of artificial intelligence, but they don't learn from new data. Machine learning, on the other hand, is completely data-driven. Which brings us right to our next layer, section 2, machine learning basics. Let's open the doll and look at the most important subdomain of AI today. This represents an absolute massive shift in how we build software. In traditional programming, a human writes the logic, right? You put in the data, the computer follows your exact logic and gives an output. But machine learning flips this entirely on its head. You feed the algorithm massive amounts of past inputs and outputs, say millions of approved and rejected bank loan applications, and the machine figures out the logic on its own. It essentially writes its own rules. Because it writes its own rules, every machine learning algorithm follows a strict two-step dance. Step 1 is training. The machine analyzes historical data, like past applicants' credit scores and salaries, to detect hidden patterns and build a working model. Then comes step 2, inference. This is when that trained model is put out into the real world to make predictions on entirely new data, deciding instantly if a new applicant should be accepted or rejected. Moving forward to section 3, 3ML categories. Within machine learning, we can neatly organize how algorithms learn into distinct buckets. Let's look at this breakdown. We can actually divide machine learning by the specific type of data it eats. As you can see, there are 3 distinct paths here: supervised, unsupervised, and reinforcement learning. Let's break these down one by one. First up is supervised learning. This uses perfectly labeled, well-structured data. We literally give the computer the answer key during training. If we feed the system thousands of emails labeled spam and not spam, it learns the exact characteristics of spam so it can classify new emails. Or, if we feed it location data and delivery times, it learns to predict numerical values, like giving you a highly accurate estimated delivery time for your food order. Then we have unsupervised learning. Here, we throw raw, completely unlabeled data at the model and basically say, hey, go find a pattern. Without any specific labels to guide it, the system just naturally groups things together. It might automatically cluster thousands of daily news articles into politics, sports, and tech. Or it might notice that shoppers who buy bread very frequently also buy milk, which, by the way, perfectly powers those frequently bought together recommendations you see on platforms like Amazon, exposing all of our weird late-night shopping habits. The third type is reinforcement learning. Honestly, think of this exactly like training a dog with treats. You have an agent interacting with an environment. When it does something right, it gets a mathematical positive reward. When it crashes or makes a mistake, it gets a negative penalty. By running millions of trial and error simulations, the algorithm learns to maximize its total reward, which is exactly how systems learn to play grandmaster-level chess or navigate highly complex self-driving cars. Next, we open up the third nesting doll, section 4, inside neural networks. This is where we leave traditional tables and spreadsheets behind and tackle complex, messy, unstructured data. Deep learning is a specialized subset of machine learning powered by artificial neural networks. And yes, it is actually inspired by the biological neurons in your own brain. Why do we need this? Well, defining the exact features of an eye or a nose in a raw image for a traditional algorithm is virtually impossible. A deep learning network, however, can extract these highly complex features from raw audio, video, or pixels entirely automatically. To understand how these incredibly complex networks actually learn, imagine a college professor adjusting their grading criteria. If students just aren't showing up to class, the professor might increase the weight of class tests to 30% and decrease the weight of midterms. Artificial neural networks do the exact same thing. If a piece of input data isn't leading to the correct prediction, the network tweaks the numerical weight of that specific connection through trial and error until the final output is highly accurate. This constant adjusting happens through an ingenious cycle. First is forward propagation. The data moves forward through the network's layers, multiplying by those weights until the model makes a guess. If that guess is wrong, it triggers backward propagation. The network calculates exactly how wrong it was, we call this the loss, and travels backward, frantically updating and fine-tuning every single weight and bias so its next guess is much closer to the mark. Now that we know how they train by constantly adjusting their weights backwards and forwards, let's turn to Section 5, Deep Learning Architectures, where we'll look at network shapes designed for different types of data. If you feed a massive colored image into a standard network, processing every single pixel at once requires millions of computations per neuron. It's just way too much. So we use CNNs, or convolutional neural networks. They scan the image in tiny patches to detect edges and shapes, making computer vision highly efficient. For text, we use RNNs, or recurrent neural networks. Because text flows in a sequence, RNNs use memory loops to remember earlier words in a sentence, so they can actually understand the flow of context. But the true breakthrough, the real game changer, came with transformers. Unlike older networks that read word by tedious word, transformers process entire sequences simultaneously. They use a brilliant mechanism called attention. If a sentence says, "The dog chased the cat because it was scared," transformers use an attention score to instantly, mathematically link the word "it" to the cat. They deeply understand context, forming the absolute backbone of modern text analysis and language models. Which brings us to the final, innermost doll in our AI hierarchy, Section 6, the generative AI era. While all the previous layers of our map were analytical, like predicting delivery times, clustering news, or classifying an image as a dog, GenAI flips the script. It takes absolutely everything the neural networks have learned about patterns and structure and uses it to generate something that has literally never existed before in the history of the world. And this amazingly structured foundation has led to a total explosion of practical tools. By using massive large language models, systems like GPT, Claude, and Gemini can instantly synthesize text. Tools like Midjourney or Sora generate stunning original images and videos. And platforms like GitHub Copilot can literally write highly complex computer code on command. It is the breathtaking culmination of decades of data, training, and neural architecture. So we've unpacked the whole doll, from the broad definition of AI to machine learning models finding patterns, all the way down to deep learning architectures powering generative magic. The next time your phone recognizes your face, automatically suggests an email reply, or flags a message as spam, you'll know exactly which layer of the AI nesting doll is doing the heavy lifting behind the scenes. So here's my question for you. How will this structural understanding change the way you interact with the technology you use tomorrow? Thanks so much for joining me on this explainer, and stay curious.